Okay, so in this video, we're going to be doing a chapter summary of differentiation, which is just from year one. So we're only looking at functions that are of this form, ax to the power of n. Now, I'm anticipating this video is going to be a little bit longer than normal because it is a pretty big and a pretty important chapter. Now we're going to start off with something called differentiation from first principles. And actually, I've put this in a little purple box here. Things in the purple box are things that are in the formula book. So we do get given the formula for this, which we'll be just using in a second. And I've actually got the curve that we'll be having a look at in this first question. So it says, find from first principles the derivative of 2x cubed. Hence, find the gradient of y equals 2x cubed when x is equal to 1. So we're talking about this point on the graph when x is equal to 1. I want to find out what the gradient is going to be at this point. Now, I've said for the exam tip here that you need to be careful to write the limit notation, which is this part here, correctly on each line, because this can cost you accuracy marks in the exam. So you don't have to start off with this beginning part, but I like to say, okay, let's let f of x be equal to 2x cubed, because that's the thing that we're actually trying to differentiate here. So we're going to be using the formula that we have. Now, if you want to, you could say dy by dx is equal to, but I'm just going to say dy by dx is equal to f dash x, which I've got from the formula, which is f, I haven't even followed my own advice, which is to be careful of this limit notation, which is the limit, and then underneath it, as h approaches 0, of f of x plus h minus f of x, all divided by h. Now I can zoom in and actually get on with what I'm trying to do. So every line needs to start with the limit as h approaches 0. And the reason we can't just make h equals 0 is because we'd be dividing by 0 at this point. And if you remember from my teaching of these videos, this is coming from like the definition of the gradient that we have. So let's actually start off f of x plus h. So that's if this is f of x plus h means we're replacing this with x plus h. So that would be two lots of x plus h all cubed, and then minusing f of x is 2x cubed, and that is all being divided by h. We still can't make h equals 0 because it would be dividing by 0. Now you're going to have to use your binomial expansion on this, and you could do it somewhere else on the page. It's a pretty simple binomial expansion, but if we have x plus h cubed, you should know that the coefficients are 1, 3, 3, 1 from your binomial topic. So it's x cubed plus 3x squared h plus 3xh squared plus h cubed. Okay, so you might want to have done that a little bit slower than what I've done, but in the sake of being efficient here, I'm going to go straight in with this. So we have the limit as h approaches 0. We have two lots of x plus h cubed, so it's going to be this thing all doubled, which is 2x cubed plus 6x squared h plus 6xh squared plus 2h cubed, and then at the end we've still got this part from before, which is our minus 2x cubed. And you can see something is going to happen in that numerator. We can see that the 2x cubeds are going to cancel because I have a 2x cubed subtract a 2x cubed. And now I've got each of these terms here all being divided by h. So I can actually write this a little bit more neatly, and I can say that the limit as h approaches 0. Now, because it's no longer a single fraction, because it's no longer a single fraction, it's multiple terms, I'm going to put a bracket to show that this limit is applying to everything inside the bracket. So I'll do the 6x squared h divided by h, which is just 6x squared. And then for the next one, it will just be a 6xh. And for the last part, it will be a 2h squared. Now we've got to this stage where we no longer have h in the denominator. We can actually just essentially substitute in h equals 0. And I'm just going to jot down what actually happens here. So as h goes towards 0, 6xh goes to 0, and 2h squared also goes to 0. Hence, we end up with just this first term, which is 6x squared. So we have 6x squared for this one, and we've actually now come up with what the derivative is. So the derivative is 6x squared. So f dash x is equal to this. And if you did it with dy by dx here instead, that would be perfectly fine as well. And then it says, hence find the gradient of y equals 2x cubed when x equals 1. So for the next part, I'm going to say when x equals 1, we can say that f dash x is going to be equal to 6 multiplied by 1 squared, which is equal to 6 times 1, which is 6. Now, if you have a look at this on the graph that we've got here, the gradient at this particular point, we're talking about almost like a tangent that would be drawn at this point. Not that I've drawn it very well at all. The gradient of this tangent should be 6, but I'm going to get rid of that because I drew it so badly. Now I have got a little note down here that you could use dy by dx instead of f dash x, and actually you could also use this y dash. You might see this less commonly, but if you do further maths, you'll see this dash notation used quite a lot more. They both represent that y has been differentiated with respect to x. Well, this one definitely with respect to x. Y dash, it could be with respect to whatever the other variable is. And f dash x represents that f of x has been differentiated with respect to x. So if you did this with the dy dx notation, it would still be absolutely fine as well. Now, when you think of differentiation, this is probably the stuff that you think of, differentiating standard functions. And I've got part 1 and part 2. I've got 4 easier ones and then 4 more challenging ones. So let's have a look at this. Let's remind ourselves of how we do differentiation. And this bit here, d by dx, that means differentiate with respect to x. And first of all, we'll differentiate y with respect to x. When you differentiate y with respect to x, you get dy by dx. People often think that you start off a differentiation sentence by saying dy by dx, but actually you're differentiating the y with respect to x. And this one, when we're differentiating ax to the power of n, where a is a constant and n is the power, you remember you bring the power down and you reduce the power by 1. Okay, so you bring the power down, meaning that you get a multiplied by n, and then we reduce that power by 1, so we get to the power of n minus 1. So you pull the power down and you reduce the power by 1. Now this only works when it's in this form. So if it's not in this form, we're going to have to do some different things when we get to stuff in year 2. So hence, if y equals ax to the n, when you differentiate each of these things with respect to x, the y actually becomes dy by dx, and the right-hand side becomes an x to the n minus 1. People think you just write that at the beginning. No, you're actually differentiating this. When differentiating, constants disappear. If you think about a constant, I don't know, for example, say 3, well, 3 is actually 3x to the power of 0. So when you differentiate this, you get 3 times 0 times x to the minus 1. You bring that 0 down, and 3 times 0 is 0. So it just completely disappears. But you can just remember, differentiation makes the constants disappear. And I sort of mentioned this, you can only differentiate terms that are in this form, this exact form. If they are not in that exact form, you need to manipulate them first. And of course, we'll be doing some things with like trigonometry and other bits in year 2. And I think we do some stuff with exponentials in year 1. So we're going to differentiate the following with respect to an appropriate variable. So our first one that we have y equals x to the 5 plus 3x4 minus 4x plus 7. Well, when I differentiate this, I'm going to do it with respect to x. The y is going to become dy by dx. We have x to the power of 5, so we'll bring the power down, and then I will reduce the power by 1. Now I have the 3x to the 4, so I'll bring the 4 down, so it becomes 3 times 4, which is 12, and I will reduce the power by 1. And then this is like a 4x to the power of 1, like this. So when you bring the power down, it's just going to become a 4 times 1. And when you reduce the power by 1, you get x to the power of 0. And if you remember, anything to the power of 0 is just 1. So it just becomes a minus 4. So if you ever have something that's like this, you can essentially just get rid of the x and just keep this part that we've got. And we said this before, when you differentiate something like a constant, like a 7, it's just not going to be there in the final answer. So we can just leave that one entirely. Okay, so for part 2 for this one, we have that y equals 2x to the minus 4. So you can do this with negative powers. The y will differentiate to dy by dx. And I'm going to pull that power down. So it's going to be a 2 times minus 4, which is minus 8. And I'm going to reduce it by 1. Careful that you're going down further. So instead of minus 4, it would be minus 5. Now for the third one, this is interesting because I deliberately did it with some different variables. I have a equals pi r squared, literally the formula for the area of a circle. Well, if you look at what we did here, we differentiated this with respect to x, this with respect to x. I think that the variable in this case is r. Pi is not a variable, pi is a constant. So I'm going to differentiate that with respect to r, meaning that a will be dA dr. It's always the order of the letters. So we have differentiated a with respect to r. It's telling you how the area of the circle is changing with respect to the radius. So pi is just like a number. So I'm going to take that 2 and pull it down so it becomes 2 pi. And I'm going to have r. I'm going to reduce it from r squared to r to the power of 1. So actually we get that dA by dr is 2 pi r, which should look pretty familiar, right? We've got the area of a circle, and then we have the circumference, which is pretty cool. Okay, and then our fourth one that we've got here, we have f of x is equal to 4kx squared minus a half x to the minus 3 plus 2. Now we know to differentiate f of x, it's going to become f dash x, and k in this particular question is obviously going to just be treated as a constant. It would probably say in the question where k is a constant, but we're going to just leave it. So I'll pull that power down, so instead of it being 4k, it's going to become 8k. Let's make that a little bit neater, that 8, so we get 8k, and I'm going to reduce that power of x from a 2 to a 1. And then here I've got the minus a half multiplied by minus 3, which is going to become a plus 3 over 2. And I'm going to reduce that from a minus 3 to a minus 4. And obviously that plus 2 that we've got there is just going to completely disappear when it's differentiated. So that was those four. Now let's try these four that need to be differentiated with respect to a standard function. I've realized I don't need this box. So in the PDF, of course, I will have got rid of that so you have more space to write it when you're trying it yourself. It's just repeating what was on the previous page. So for the fifth question, we have that g of t equals the cube root of t. Now this obviously is not written in the standard form here. So I'm going to begin by writing it in the standard form. The cube root is to the power of a third. So then when I differentiate this, I'm going to differentiate with respect to t. I will pull the power down and I will reduce the power by 1, and a third minus 1 is minus 2/3. So we get 1/3 t to the power of minus 2 over 3 for that one. Okay, so the next one, number 6, it's not in the standard form, so I'm going to have to first of all begin by expanding the brackets on the right hand side because it's not in that standard form. So I will get a 2y squared. I will get a 3 times 2y, which is 6y, a y times minus 1, which is minus y, and then I get a minus 3. So, before my iPad jumps all over the place, x is 2y squared plus 5y minus 3. Now, we normally differentiate with respect to x. I think the appropriate variable in this case is going to be to differentiate with respect to y. So we would get dx dy instead. I'll pull the power down. 2 times 2 is 4, and reduce the power by 1. The 5y is just going to come to a 5, and the minus 3 is obviously just going to disappear. So the seventh one that we've got, we have v equals the square root of t. I think the square root of t I'm going to rewrite as t to the half, and I get a 4t squared, and this is being divided by 2t to the third. Now it's not in that standard form, so I'm going to need to do each of these things divided by 2t to the third. So I will begin by concentrating on this one and this one. Remember, you subtract the powers, so I'll do a half subtract a third, which I think is a sixth, but my brain has been a bit slow this morning, so it's definitely going to be a t to the power of a sixth. Sometimes people think it's a 2, but clearly the 2 is in the denominator, so it won't be a 2, it will be a half. And then for the next part, we have the t squared and the t to the third, so I'll do 2 minus 1/3, which is 5/3, so it will be a t to the 5/3. And we have a 4 divided by a 2, which is just a 2 in this particular case. So we're going to now differentiate, and the variable we'll differentiate to will be with respect to t. So we get dv dt, and if you've done mechanics, I want you to think, what is dv dt? It's how the velocity is changing with respect to time. It's the acceleration. So we'll differentiate this. I will pull down this power, so I'll have a half times a sixth, either on your calculator or in your head, is a 12th, and I will do 1/6 minus 1, which is minus 5/6. And then I'll do the 2 times by the 5/3, which is obviously 10/3. And I will do 5/3 minus 1. 5/3 minus 1, that's 5/3 minus 3/3, which is 2/3. So we get 1/12 t to the minus 5/6 plus 10/3 t to the 2 over 3. You can see how they get a lot more complicated than what we did on this first slide here. And then our last one, our eighth question. This one looks like it's talking about the population of something because I've got a capital P here. And I have 1 minus 5t squared over t cubed plus 5, something to do with some kind of population. So when I differentiate this, when I get dp dt, I will be having the rate of change of the population, but it is not in the correct form yet. So I'll have to do this divided by this. 1 divided by t cubed, that is 1 over t cubed, which is obviously just t to the power of minus 3. And then there's going to be a minus 5. I have a t squared and a t to the 3. That'll be t to the power of minus 1. And I still have that plus 5 like this. So when I differentiate dp dt, I will pull that power down, so it becomes minus 3, and I will reduce it by 1. I will do a minus 5 multiplied by a minus 1, which is a plus 5. That's me pulling the power down, and I will reduce the power by 1. And obviously this 5 will go to nothing, and we end up with the statement that dp dt is equal to minus 3t to the minus 4 plus 5t to the minus 2. Okay, now let's talk about some graphical interpretation about the first and second derivatives. I'm going to begin just by talking about the first derivatives that we have over here. Now, they actually tell us about the gradient of the function, and I've got a couple of different things on here. I've got a line, and I've got a curve, and we'll talk about these different things. So dy by dx being equal to 0, well, that is talking about places where the gradient is 0. Okay, so the gradient is 0 would be referring to this place here. That has a gradient of 0. This place here has a gradient of 0. I'm just drawing on some tangents to these curves. And of course, we can see that this flat line has also got a gradient of 0. So this one has a gradient of 0. It's got a gradient of 0 here and here. We call those stationary points. This one is a stationary point, and a stationary point, we also call those turning points as well. Okay, so it's something that has a flat, and I'm going to say that it is a stationary point. Now, if the gradient is less than 0, it's something that is sloping downwards, and we would call this a decreasing function. So let's just see some places where there's going to be a decreasing function, where you can see in this whole section down here, it is sloping downwards, so that is an area where there is a decreasing or a negative gradient. Obviously, if the gradient is greater than 0, we would say that it is an increasing function. And if it's an increasing function, it's anywhere that it's got this kind of positive slope. So this whole section down here, that is a positive gradient. This whole section here has got a positive gradient. Now, there's one thing we haven't talked about, which is this line here, which is this vertical. dy by dx is undefined. That is when we have a gradient that is like this. That is vertical. You don't really come across that until perhaps a little bit later in year 2 differentiation, but we would say this gradient here is undefined. If you try and think about how you do the gradient like back in GCSE, there's no change, there's a change in y, but there isn't a change in x. So you get dividing by, change in y over change in x, you get dividing by 0, which is why it's undefined. So I just wanted to show you can put this into context with other things where you might need to find a tangent and a normal. Maybe the idea of a normal is maybe the first time we kind of come across it here. The normal is like a perpendicular to a tangent. So we have y equals a half x cubed plus 3 over 2x squared minus 2x plus 1. We want to find both of these tangents and normals at this point. So I'm going to begin by differentiating so that dy by dx is equal to, I will pull that power down, so I get 3 over 2. Reduce the power by 1. For the next one, I'll do 3 over 2. I'll pull the power down. 3 over 2 times 2 is 3. And when I reduce the power by 1, I get x. We then get a minus 2, and then the 1 doesn't do anything. So when x is equal to 1, let's find out what the gradient is equal to. The gradient would be 3 over 2 times by 1 squared plus 3 times by 1 minus 2. So what's that? That's a 3 over 2 plus 3 minus 2. It is 5 over 2. Now, if you want to find out the equation of the tangent to a particular curve, we know what we have to do for that. You literally just have to find a coordinate, and then you just use the gradient. So we need to find a coordinate when x is equal to 1. When x is equal to 1, let's find out what y is. It would be, using this statement here, it would be a half times 1 cubed plus 3 over 2 times 1 squared minus 2 times 1 plus 1. So that is a half plus 3 over 2 minus 2 plus 1. It's also 1. So the coordinate is 1, 1. So we can go straight in and we can find the equation of the tangent using y minus y1 equals m brackets x minus x1. So it would be y minus 1, we're talking about this is x1, y1, is equal to the gradient, which is 5 over 2 x minus x1. Now, the normal is something that is perpendicular to the tangent at that point. So it would be the same as y minus y1, but we would take the negative reciprocal here as minus 2/5 x minus 1. And if you want to, you can put this on a graph and you can see, I might actually add it into the PDF if I can squeeze like a small diagram in so you can see that one is a tangent and one is a normal. Okay, so we've now got a different one, which is to do with second derivatives and stationary points. So I'll come back to the question in a second. But here we're going to be thinking about the second derivative. Second derivatives is literally just when you take dy by dx and you differentiate it again, and we use just this slightly different notation here. it tells you about how the gradient is changing. The first one tells you about the gradient. The second one tells you how the gradient is changing. So if we look at this part here, it's very, very positive gradient. It then goes to 0 and then it goes to negative. So the gradient is decreasing because it's going from positive to 0 to negative. If something is going from positive to 0 to negative, it is decreasing. It is talking about this one. So in this whole section here, we are talking about the gradient is decreasing. So we would say this is the section where that's happening, but we're only interested in the stationary point. At this particular stationary point that we've got here, we would say that the second derivative is this one. It is the maximum point. So we call this a local maximum point. It's a local maximum point for a stationary because there might be another maximum point somewhere else, but we're just saying in this area. Now, the way I remember this is I always think of like a little person stood at this stationary point, and everywhere they look, it's going downhill. Everywhere they look, there is a negative gradient, and that's how I remember it in this particular way. Now, in this case, we're talking about it being greater than 0. If you look over in this part, it's going from a negative gradient to a 0 to a positive, which means if something's going from negative to 0 to positive, the gradient is increasing, hence it being positive. We would say that this is a local minimum point. We're talking about this point down here for the stationary points. And again, the way I remember this, I think of like a little person stood at the bottom of this valley here. If you're stood at the bottom of the valley, that looks positive and that looks positive. They both look like they're going up, which corresponds to this positive here. Now, if we have the second derivative at a particular stationary point being equal to 0, it could be a max, a minimum, or a point of inflection. So this one needs to have further investigation. And the way that you would investigate this is you'd look at dy by dx either side of the stationary point. So it could refer to this one because you have positive over here and negative, but it requires further investigation, and you'll see there's some more techniques for that in year 2 as well. So let's have a quick look at this one. It says a curve has this equation. We're going to find the first and second derivatives. Okay, nice and easy. I'll go quite quick for this first one. So I'll differentiate this to get dy dx. So I will bring the 2 down and reduce the power by 1. I will get the minus 3. Might help to write this as minus 20x to the half. So I'll do the minus 20 times the half, which is minus 10. And I will do the minus the half, take away 1, which is minus a half. And then I will do the second derivative like this. And that needs to be differentiating this thing. So I'll pull this down. 2x differentiates to 2. The 3 is going to disappear. The minus 10 times by minus a half is a plus 5. And we get x to the power of, what will that be? Minus 3 over 2 for that bit. It then says for part B, verify that it has a stationary point when x equals 0. So a stationary point, that means that the gradient is 0, as we talked about on this part up here. These things are referring to the stationary points where the gradient is 0. Now, it doesn't say find it, it just says verify. So this just means we can say when x equals 4, we can literally just substitute it into dy by dx. So that's 2 times by 4, minus 3, minus 10 times 4 to the power of minus a half. I'll check it on my calculator very quick. That's 8 minus 3. Minus 10 times 4 to the power of minus a half, and we do get 0. Now, you do need to confirm this and say, hence, it is a stationary point, so that they understand that stationary points are when the first derivative is equal to 0. And then for part C, it says determine the nature of this stationary point, giving a reason for your answer. So the nature of the stationary point is asking, is it a maximum, is it a minimum, or is it some kind of further investigation that is required? So I think what we'll do is we now just substitute x equals 4 into this one. So I'm going to say when x is equal to 4, the second derivative is 2 plus 5 times by 4 to the power of minus 3 over 2. And it's very quick to tell. That's obviously going to be positive. So you don't even need to work it out. We can just say it's greater than 0. So we can say as the second derivative is greater than 0, it is think about the gradient being greater than 0, you're looking up everywhere. That means it is a minimum point. Hence, it is a minimum point. You could say local minimum, but minimum point would be perfectly fine for this one that we have. Okay, and then to finish off, we're going to do an optimization problem. This is one of the most common ones that there is in an exam paper. And I've written in this blue box that differentiation can be used to find maximum or minimum points for functions. which corresponds to optimal solutions for solving real-life problems. People do use this a lot in real life, but often the context of an exam question doesn't feel very real. So it's like the stuff we're doing on the graph, apart from we're no longer doing it on a graph, we're visualizing it or trying to do it for some other kind of function. So the cost, C pounds, of a chemical process is modeled by this equation, where T is the controlled temperature of the process in degrees Celsius or centigrade. Using differentiation, find the temperature which minimizes the cost, the corresponding minimum cost, and confirm by differentiation it is a minimum. So we want to make this chemical process, we want to make it as cheap as possible. So we will try and make the temperature a particular temperature to keep this process as cheap as it can be. So I should begin by writing this in its kind of standard form. I wouldn't write that as 200 over T. I would write that as 200 T to the minus 1. And then this is T over 10. I guess if we want to, we could just put that as like a decimal, or maybe we just do it as a tenth. However, it doesn't really matter, but I'll write it as the 10th T, and then I have plus 12. So by differentiation, this means I'm going to differentiate this to try and find a stationary point where there is like a minimum kind of cost. So I will pull the power down, so it becomes minus 200, and I will reduce the power by 1, and then I will do a 10th T, that's just going to differentiate to a 10th, and then the 12 is just going to disappear at that particular bit. So because we're looking for a minimum cost means that dc dt is going to be equal to 0. Now, it could obviously be a maximum cost if dc dt is equal to 0. If you've got a curve, we're looking for this minimum one, but you might get given a maximum, which is why at the end we're going to confirm that it is indeed a minimum. So we need to make this thing equal to 0, so that's minus 200 t to the minus 2 plus 1/10 is equal to 0. So I'll put the 200 t to the minus 2 on this side. And if you think about what that looks like, that's the 1 over 10, 200 over t squared. So I'll multiply it by the t squared, and then I'll multiply it by the 10. So I get that t squared is equal to 2000. And so t is the square root of 2000, which is 44.7 degrees Celsius. And I've just done that to 3 significant figures that we've got here. But on my calculator, it did initially come up as 20 root 5, which might be useful to use for substituting later on. So that is the minimum temperature that minimizes the cost. Now we're going to find the minimum cost. Now we're going to use the original formula for this, which is this one. So that would be C equals 200 multiplied by 44.7 blah, blah, blah to the power of minus 1. Plus a 10th times by 44.7 ... plus 12. And that bit that I've got here, I've just got that on my calculator already, so I can just type it straight in. So that's 200 times by the answer to the power of minus 1 plus a 10th times by the answer plus 12. And we get that the minimum cost is £20.94. So I'll say the minimum cost is £20.94. And we just need to confirm now that this is a minimum. And the way we can confirm it's the minimum is by, of course, using the second derivative and hoping that we get that the second derivative is greater than 0. So I will go to the part, this thing that we have here, and differentiate it again. So we get d2c dt squared. So I will take the minus 200 and multiply it by minus 2. So it will become a 400 t to the minus 3 plus 1/10. When t is equal to 44.7, we get this thing. It's pretty obvious now. It's going to be positive. It would be 400 times by 44.7 to the power of minus 3 plus a 10th. I guess I could put it on my calculator anyway, just to show you that it's definitely positive. I've got it as 0.104 something. As long as I've typed that into the calculator correctly. Oh no, I think I've differentiated this wrong, haven't I? When I differentiate this, obviously that disappears. So I don't want that there at all. Or that. So if I get off that 10th, it would just be 0.004 like this. Very silly, not even following my own advice there. Might come up on standard form in your calculator, but that's fine. And we can say that this is greater than 0. Hence, the cost is a minimum. Okay, So a lot to do in differentiation. Really, this is one that a video like this isn't going to be enough. You have to go and practice these questions. If you don't practice them, you're not going to get good at this skill. And it is an incredibly important skill, particularly as you move forward into year 2 stuff. So if you're finding this useful, please do make sure you're subscribed to my channel. I'm trying to get to 100k subscribers. Lots of people are watching and not subscribed. It will take you 2 seconds and it'll make a big difference for me. Good luck with your studies, and I hope to see you in another video soon.